Now we're going to talk about something called enthalpy, which kind of sounds like you're lisping, but enthalpy. This is the heat that's evolved at constant pressure, as opposed to what we were looking at before, which was constant volume. So if we have a chemical reaction in a container that's open to the atmosphere, so constant pressure, atmospheric pressure, energy can be evolved as both heat and work. Most of the time, we're only interested in the heat exchange. We don't care about the work. So the enthalpy, which is given the symbol H, is the sum of the internal energy and the product of the pressure and the volume. So H is equal to the internal energy plus the pressure times the volume. Enthalpy is a state function, like internal energy, like pressure and volume. It doesn't matter how you got there. So if we want to look at the change in enthalpy, delta H, change in H in enthalpy is going to equal the change in internal energy plus pressure times the change in volume. The pressure's doesn't have a delta here because this is at constant pressure. So we learned earlier that the change in internal energy is the sum of the heat plus the work. Here this Q has a subscript of P, meaning constant pressure. So we have Q plus W plus this P delta V thing. Well, remember, work is equal to negative P delta V. So this piece right here is equal to negative W, and the W's go away. It's magic. It's math magic. And we end up that the change in enthalpy is equal to the heat at constant pressure. Enthalpy and internal energy they're hard to distinguish. And at the level of Chem 1A, it doesn't really matter. They're very similar in concept, and often they're also very similar in value. Delta E is the measure of all the energy that's transferred, both heat and work, and delta H is a measure only of the heat exchanged under constant pressure. But most of the time, they're essentially the same. The only time there's a significant difference is when you have reactions that either produce or use large quantities of gas, so you get big volume changes. But we're not going to do any of those. So delta H and delta E are different things, but if they get fused in your brain as a single thing, it's okay. I'm not going to ask you what the difference between them is. Having said that, this problem, lighters are usually fueled by butane. When 1 mole of butane burns at constant pressure, it produces 2,658 kilojoules of heat and does 3 kilojoules of work. What are the values of delta H and delta E for the combustion of 1 mole of butane? I would never ask you this question on an exam, but since we were just talking about it. Delta E is heat plus work. Delta H is only the heat. So in this problem, this is the heat, right? We have 26.58 kilojoules. Is that positive or negative?
Positive.
For the system? Is it leaving the system or coming into the system? It's leaving the system. So Q for the system is going to be negative. And then we've got 3 kilojoules of work. The system is doing work. Is that positive or negative? Do you like doing work?
Negative.
It's negative. Do you like it when people do your work for you?
Yes.
Yeah. Okay, so both of those are negative, right? So delta H is going to be equal to Q, right? So it's negative 2658, and the first 3 are all negative 2658, and this one's wrong because it's positive. So we can eliminate that one. Because delta H is equal to Q at constant pressure. Delta E is equal to Q plus W. So when we add these 2 together, what do we get? Negative 2,661 kilojoules. So that's the correct answer. This one's just looking at the work, and this one got one of the signs wrong. So the signs for delta H and delta E follow the same conventions. If heat is leaving the system, that's negative. If heat is coming in, it's positive. So when delta H is positive, heat's being absorbed by the system, heat is coming in, we call that an endothermic reaction. Endothermic. So thermic relating to heat, right? When delta H is negative, heat's being released, and we call that an exothermic reaction. Okay, so exo is kind of like exit. And what do you do at the exit? You go out, right? Exothermic means heat is leaving the system. Endo is a little bit like the word into. Into heat. Heat's coming into the system. Okay? They're easy to confuse. We talked about the chemical hand warmers. Let's just skip to those guys. So those chemical hand warmers have iron filings that oxidize with the air, and that's an exothermic reaction. It's giving off heat. Our hands are part of the surroundings, and we get the heat, right? Burning natural gas, another example of an exothermic reaction. So a Bunsen burner or your gas stove or your gas grill, you light the gas and it gives off heat, right? This is the point of it, is to give off heat. So the system is the gas burning, and that's releasing heat into the surroundings, which is where we are, and we feel the heat. They also have these instant cold packs. I was going to say they're kind of cool, but that's just stupid. Thank you for that. I appreciate it. So those have ammonium nitrate in them. And when you break that seal in there, water mixes with ammonium nitrate, and as that dissolves, it's an endothermic process. The reaction absorbs heat. Where does it get the heat from? The surroundings, right? So if you have a sprained ankle and you put this package with this reaction in it on your sprained ankle, it's going to take heat away from your ankle, right? It's going to cause it to become cooler. Any questions about that? So identify each process as endothermic or exothermic and indicate the sign of delta H. So an ice cube melting. Okay, so that was surprisingly tricky, right? We've got some disagreement here. So let's think about what would make the ice cube melt faster? If we heated it or if we made it colder? If we heated it, right? So that would be putting energy into it.
Oh, so endothermic.
Endothermic.
Okay.
Yeah. So this one's endothermic. And these sorts of questions are great for exams. So if it's endothermic, what's the sign of delta H? Positive. Because heat is going into it like money going into your account. It's a good thing. It's positive. So delta H is positive, meaning delta H is greater than 0. Okay, nail polish remover quickly evaporating after it's accidentally spilled on the skin. I'm going to let everybody think about it a little bit. How does that feel? It's like alcohol. Like alcohol wiped on your skin for a shot. Does that feel warm or cold? Cold. If anybody wants to feel it, nail polish remover, it's cold.
Because heat's leaving the surface.
Well, why does my hand feel cold?
Heat's leaving.
Heat is leaving my hand and going where? Into the process, right? So again, this one's endothermic.
Okay.
Yeah. So endothermic, and so delta H is greater than 0. Gasoline burning within the cylinder of an automobile engine. Exothermic. I think we all know that the engine of a gas-powered car gets hot, right? Why does it get hot? Because the combustion releases energy, right?
So
It gets
more like if you touch it, do you feel cold or hot? If you feel hot, then it's exothermic. If you feel cold, then it's
pretty much, yeah, pretty much. So here, delta H is negative because the energy is leaving the system. Okay? And with these things, it's good to just kind of take a step back and think about it, right? Because it can get confusing. Okay, so an exothermic reaction is giving off thermal energy. Where does it come from? So the substance contains internal energy, which is kinetic energy, and potential energy. So it's got to be one of these, or possibly both. It can't be kinetic energy because the kinetic energy is a measure of the temperature of the substance. And if it was losing kinetic energy, it would get colder, but it doesn't, right? It gets hotter. So what happens is that when atoms are rearranging in the chemical reaction, their potential energy, their chemical potential energy, gets converted into thermal energy. So we have weak bonds that get broken, strong bonds are formed. When a strong bond is formed, it releases a lot of energy. When a weak bond is broken, you have to put in a little bit of energy to break the weak bond, and then the strong bond forms and that releases a lot of energy. So really these exothermic reactions involve breaking weak bonds and forming strong bonds. And then there are also endothermic reactions like ammonium nitrate dissolving in water, right, that pull energy in. And so there you're breaking the big strong bonds and you're making weaker bonds. And so, yeah. Any questions? Okay, so an endothermic reaction occurs in a flask. What happens to the temperature of the flask? Is it going to get hotter? Is it going to get colder? Or is the temperature going to be unchanged? An endothermic reaction.
I mean, inside the flask?
So the reaction is inside the flask. You could assume that it's in contact with the flask. So which direction is energy going in terms of the reaction?
Right? No, because
It's an endothermic, endo into,
yes.
right?
Into.
Into.
But it means the
So yeah, delta H would be positive. So energy is coming in. Where does the energy come from?
outside.
Outside.
So
Right.
outside the temperature falls, but inside it rises. No?
Well, outside the temperature falls. You really can't measure the temperature of the reaction itself.
Okay.
Yeah. Because like a lot of chemical reactions occur in aqueous solution, right? They're dissolved in water. How do you measure the temperature of the individual ions
Right.
separate from the
So
water?
it's always outside. Right?
Yeah,
Okay.
yeah. So the temperature of the flask would fall
Uh-huh.
because the flask is losing energy to this reaction that's occurring. So we can do stoichiometry again with energy. So enthalpy change for a reaction, delta H reaction. That's also called the enthalpy of reaction or the heat of reaction, which then, the H kind of makes more sense. Heat of reaction. So this is an extensive property. It depends on how much stuff is reacting, right? So if you think about 2 drops of gasoline burning versus 500 gallons, which is going to give off more energy? The larger, right? The more gasoline you burn, the more energy you get. It depends on how much, right? So it's extensive. So when we look at a chemical reaction, here's propane combusting with oxygen. And this is saying delta H for the reaction is negative 2,044 kilojoules. For how much propane? By convention, when we say delta H and it's associated with a chemical equation, we mean that we get this much for the stoichiometric amounts of moles. So this is 1 molecule of C3H8 or 1 mole of C3H8. So if you burn 1 mole, 2,044 kilojoules, or 5 moles of oxygen. If 3 moles of carbon dioxide are produced, or if 4 moles of water are produced, that's the amount of energy that's released. So we can use this as a conversion factor between kilojoules and moles of reactants or products. So let's look at this thermochemical equation. It's a thermochemical equation because it talks about the heat. It gives the heat of reaction here. So we've got 2 atoms of A are forming 1 molecule of A. Or we could interpret that as 2 moles of A atoms are forming 1 mole of molecules. Right? Delta H is negative 51 joules. So what's the heat associated with the reaction of 6 moles of A? This is the amount for 2 moles. How many times bigger is 6? 3 times bigger. So then for 6 moles, we must have negative 51 joules times 3, right? Negative 153. Does that make sense? 3 times as much stuff, 3 times as much heat. Okay. Ammonia reacts with oxygen according to this equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. We have a chemical equation, and we're talking about amounts of stuff. I wish that guy would just rev his car and go away. I don't know what he's trying to prove. This is stoichiometry. So where do we start with stoichiometry? Grams to moles to moles to grams, right? Every time. Grams to moles to grams. And then we just see, do we need to change it or can we use it just like that? Well, I kind of skipped over highlighting the numbers. So we have 155 grams of NH3, and we're asked for the heat in kilojoules. So this is what we're starting with then, right? So that's a mass of ammonia. So we can take mass of ammonia to moles of ammonia, and this is where the thermochemical stoichiometry gets a little easier, because this amount of kilojoules is for 4 moles of this, or 5 moles of that, or 4 moles of that, or 6 moles of that. We don't have to go from moles of ammonia to moles of product and then to grams. We can skip both of those steps and go straight to kilojoules. Because in terms of moles of ammonia, which is what we're going to be talking about, this is negative 906 kilojoules for every 4 moles of ammonia. The chemical equation is telling me that. Any questions about that? So I've got 155 grams of this, and I'm trying to find energy. So 155 grams of NH3, and I'm going to convert that to moles of NH3. And then I know the relationship between moles of this and the energy, so I can go directly to the kilojoules. So I get grams of NH3 down here, and moles of NH3 down here. Grams and moles, that's molar mass. And then this, just like the mole-to-mole ratio, comes straight from the equation. You just read it off. How many kilojoules? Negative 906. How many moles of ammonia? 4. 4 moles of ammonia. The place I mess up the most often is when I'm doing the math, I forget to divide by that number. I don't know why, but I do it. So 155 divided by 17.034 times negative 906 divided by 4 is equal to negative 2061.025 blah 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 kilojoules. We should have 3 significant figures. So a not so great way of doing it is saying negative 2060. It'd be better to say negative 2.06 times 10 to the third kilojoules. Any questions? So that was finding the heat when a certain amount of substance reacted. This is saying we need a certain amount of energy. How much butane do we need to burn to get that? What mass in grams of butane is necessary to produce 1.5 times 10 to the third kilojoules of heat? And then another question, what mass of CO2 is produced? So the number given there is 1.5 times 10 to the third kilojoules. And we've got two questions. Mass of butane in grams and mass of CO2. So 1.5 times 10 to the third kilojoules. And I want to know how many grams of this and how many grams of that. So we're going to start with grams to moles to moles to grams. The unit I'm starting with is kilojoules, right? So I'm not starting with grams. I'm ending with grams though, right? So I'm going to end with grams. Do I need to do a mole to mole conversion with the energy? No, because this relates to any of those. So I can skip this one and I can start with kilojoules, go to moles and to grams. (1.5 times 10 to the third kilojoules). We'll do the first question first, the mass of butane. So I'm going from kilojoules to moles of butane. Kilojoules will come down here, so those cancel out. And then I'm going to go to grams of butane, and moles of butane will come down here. So the mole to kilojoule relationship, there's 1 mole of butane, and negative 2658 kilojoules. And then over here, I need the molar mass for butane. Four times 12.01 plus 10 times 1.008, 58.12. So 58.12 grams per mole. 1.5 EE3 divided by negative 2658 times 58.12. And my calculator says negative 32.799 grams. That's not a Q, that's a G. Is that okay? We can't have negative mass. What happened? Produced. It was producing this much heat. So that should probably have a negative sign because it's being produced, right? So then if we do that, now we get a positive number. And 2 sig figs. So 33 grams of butane needed. That's the first question. The second question, we're calculating a mass of one of the substances again. So now we know we should put that negative sign there. Kilojoules. And now we're going to convert to moles of CO2. And then grams of CO2. So make sure that our units are canceling out. So the moles of CO2, how many moles of CO2? 4 moles of CO2 for that same amount of energy, negative 2658 kilojoules. And then here we need the molar mass of carbon dioxide. So 44.01. So negative 1.5 EE3 times 4 divided by negative 2658 times 44.01. 99.35 grams, so 99 grams of CO2 would be produced. Any questions?
If you did that second mass with the molar ratio of like just the reactants, would they throw your answer off? Is that doable? Or like instead
If I used 1 mole of this to 4 moles of that,
yeah.
well, you could take this part here and go off on a tangent.
Because I know we were doing that, well, I guess that's, if it works out, it's just another way.
Right. So this is what I think you're saying. Let's just cover that
Just
up.
go off of like the reaction coefficient ratios.
So, well, actually, since I can, get rid of that as well. And then put in here moles of CO2 to moles of butane. And then you're going to have to multiply by the mass. You can do that. It's just going to take you another step. 33 grams, 99 grams.